Hello, and welcome back. Before we begin today's discussion, if you haven't seen my previous video, The Unification of Gravity and Electromagnetism, then I strongly suggest that you first view that video before you view this video. Now today I will be giving you the quickie and proof or explanation of the Navier-Stokes equations. This proof is extremely long and fairly complicated. And it's complicated not so much because of any murky concepts, but because of its sheer length. And since it is so long in length, that makes it impractical to try and fit it all within a single video. So this video will not have very many derivations or detailed explanations. It will essentially tell you what the Navier-Stokes equations are and several corroborating equations to verify it. This proof, or more precisely this explanation, will be compact and concise. But to make up for this shortfall in explanations and derivations, I've written an official paper that provides the proof to the Navier-Stokes equations conundrum. It is entitled Gyroscopic Interpretations of the Navier-Stokes Equations. I can't recommend strongly enough that you purchase this paper. To get maximum value from the video content, it should be viewed and studied in conjunction with the paper. This paper essentially combines video 7 and video 8. It is 81 pages in length and comes complete with an abstract and bibliography. It is currently priced below $15, which is considerably cheaper than just about any paper you can purchase from any reputable journal. I have not submitted this paper to any journal. You as my audience would serve as my peer review. In the end, it is the algebra that is the final arbiter. The algebra should be self-evident. If it is not, then simply reject it. Again, follow the rules, be logical, and use common sense. Proof of the Navier-Stokes problem is also listed in synthesis. We are now ready to continue our journey. We first ask, what are the Navier-Stokes equations? Well, conventionally, the Navier-Stokes equations are a group of equations that describe the motion of a fluid in space, be that fluid a liquid or a gas, through the application of Newton's second law and the law of conservation of mass. Secondly, we ask, why are we interested in these equations? Simply put, our interest is due to a variety of different reasons. It expands our knowledge of the physics of fluids, to obtain fame within the field of mathematics, and last but not least, $1 million prize for providing the solution. The Millennium Prize problems are 7 mathematical problems selected by the Clay Mathematics Institute. The Institute will award $1 million to anyone who can solve any of these 7 problems. One of these problems is the clarification and elucidation of the Navier-Stokes equations. The problem has been divided into 3 parts. Those 3 parts are as follows. Now what follows will be a quick algebraic explanation of the Navier-Stokes equations. Most of the algebraic equations will be given without first being derived. All the equations can be verified by doing a dimensional analysis on the equations. This is of course complicated and very time-consuming, but one benefit of such an analysis is that it ensures that you actually understand the origin of the equation. Having said that, you will most likely find that it is still much more useful and far less time-consuming if you refer to the paper when studying these algebraic equations. And so in a nutshell, we can briefly summarize the Navier-Stokes equations as simply being an expression of the standard Quaternion equation Ij equals K. The Navier-Stokes equations are equations that sum the gyroscopic forces acting within and upon the plus or minus 1 unit spheres, which ultimately is and must be an expression of Euler's formula. In its most compact form, it is simply the quaternionic expression Ik equals minus J. The Navier-Stokes equations manifest in a variety of different forms. Those forms being Johnson's law of vorticity, the Hildebrand solubility parameter, the summation of the gyroscopic forces, the Rodriguez rotation formula, and the Quaternion rotator. Fluids and gases generally exist while occupying some volume of space, and that ijk volume is the Quaternion, -1. Fluids and gases are governed by the Navier-Stokes equations because volume, just like direction, exists as an independent physical state. It is important to note that volume or space is not some inert stage upon which the actors of physics play their parts. Space itself has agency. It exerts its influence upon anything that exists within or upon it. Space flows. It possesses a frequency, a flow rate, a vorticity, a turbulence, and is therefore time-dependent. It assumes the form of the Quaternion rotator, which is given by the following equation. Or conversely, but equivalently, it is governed by Johnson's law of vorticity. This equation was derived in the previous video, and which is also derived in the paper. Johnson's law of vorticity unifies the scalar forces of gravity, electrostatics, and magnetism. The very act of some particle occupying a volume or the unit sphere imposes upon that particle an axiomatic fealty to all the rules and principles of quaternions, and therefore all the rules and principles of quick and quaternion mechanics, which brings us back full circle to a previously derived axiom. The physical function of a quaternion cannot be divorced from the algebra that defines it. Therefore, since Johnson's law of vorticity, and by extension the Navier-Stokes equations, may all be described algebraically as being Quaternion rotators, then they will and must behave physically as a rotator. Space, as volume, possesses a resistance to other flows. Space is a quaternion, and as such, by definition, is a particle undergoing constant precession, which in turn imparts upon it an innate ability to precess other quaternions. It is an all-pervasive particle acting as the universal UQ, or unit quaternion, which constantly precesses that with which it interacts. Dimensional analysis establishes that the Navier-Stokes equations are equations of force per volume, or equivalently vorticity. And since the direction of vorticity spin may be infinitely variable, then the Navier-Stokes equations must be descriptive of any vorticity or spin attached to any vector or quaternion that exists within the confines of the plus or minus 1 unit spheres, no matter the direction of the axis about which the quaternion spins or rotates or precesses. This is precisely the function of the Rodriguez rotation formula. The formula describes the rotation of any vector about any axis in any dimension. Therefore, the behavior of a particle governed by the Navier-Stokes equation is completely described by the Rodriguez rotation formula. We may now list the various elements that satisfy the first condition of the Navier-Stokes equation's Millennium Prize problem. The Navier-Stokes equations sum the gyroscopic forces that exist and exert within the plus or minus 1 unit spheres. The Navier-Stokes equations equals IK equals minus J. Johnson's law of vorticity sums the gyroscopic static forces, which is given by the following equation. The Navier-Stokes equations sum the gyroscopic cylindrical components of force, which is given by the following equation. The Navier-Stokes equations are equations of entropy or vorticity. The Navier-Stokes equations sum the scalar forces that operate along the x-axis as well as the vector forces that operate about the circumference. Negative scalar forces are equivalent to entropies. The sum of the three scalar forces, that is Michael's law, which is equivalent to Newton's gravitational force law, Crew's law, which is equivalent to Coulomb's law, and Maxwell's law of magnetostatics equals Johnson's law of vorticity. The confluence of these four equations form an ICR, which is the intersection of the space and body centroids, which is the entrophitic form of the mass continuity equation. The Hildebrand solubility parameter is defined as the square root of the cohesive energy density and is defined as follows. Therefore, we obtain the following equations. Since vorticity is equal to the square root of entropy, then vorticity is also equivalent to the Hildebrand solubility parameter delta. Therefore, we may state that since entropy equals vorticity squared, then entropy equals delta squared. Therefore, we obtain the following equations. To dissolve a material, its cohesive energy density must be exceeded. That is, its molecular or ionic bonds must be cleaved. Solubility parameters indicate a substance's susceptibility to being dissolved as well as its miscibility with other dissolved substances. Therefore, the Navier-Stokes equations may also be considered as the square of a Hildebrand solubility parameter. We may now satisfy the second condition of the Navier-Stokes equations Millennium Prize problem. If the solutions to the Navier-Stokes equations are expressed in terms of Euler's formula, as they must, then the solutions cannot and will not grow without limit. Their values can only oscillate between plus or minus 1 within or upon the plus or minus 1 unit spheres, since in quick and quaternion mechanics, infinity does not exist. In the plus or minus 1 unit spheres, there are only the boundaries plus or minus 1, plus or minus 0, plus or minus 1/2, and the numbers as quaternions that occupy the spaces between these boundaries. Within the plus or minus 1 unit spheres, plus or minus 1, plus or minus 0, and plus or minus 1/2 are all equivalent. Therefore, the very fact that the continuity equation equals 0 axiomatically restrains it to the confines of the plus or minus 1 unit spheres. Therefore, the Navier-Stokes equations cannot and will not grow without limit. The Navier-Stokes equations represent the total sum of the forces being applied throughout an isotropic unit sphere. Isotropic means that the pressures being exerted within or upon the plus or minus 1 unit spheres are being evenly distributed. If the pressure throughout the sphere is isotropic, then the force per volume is the same as force per area, is the same as force per line, is the same as force per point. The invocation and application of entropy allows for the accommodation of this isotropic requirement. This isotropic requirement, when applied to the quaternion as derivative, obviates the need or concept of the partial derivative, since the Navier-Stokes equations and Johnson's law of vorticity, compute entropy per particle. There is no need to compute the energy of force along each of the three separate individual axes, since the computed entropy inherently encompasses the three axes in the form of the quaternionic volume. Therefore, e to the I theta is equal to entropy, which is equal to vorticity squared. The Quaternion rotator is defined as being the strain and is given by the following equation. Entropy axiomatically computes the forces being exerted in all of the four dimensions that exist within the plus or minus 1 unit spheres and is given by the following equation. Entropy completely obviates the need for the partial, or nabla, or the divergence operator, or the curl operator. Strain, or the Quaternion rotator, is defined as being dimensionless. Conjugate strains produce equal changes of volume. Strain and quaternions as radians are dimensionless and are therefore ideal candidates for establishing isotropic conditions. By allowing the Navier-Stokes equations to be represented by a dimensionless quantity such as strain, we therefore obviate dimensional inhomogeneity, ensure dimensional homogeneity, and verify the fungibility and miscibility of all quaternions within or upon the plus or minus 1 unit spheres, no matter the ostensible physical dimensions that may define them. Therefore, entropy may acquire a variety of different dimensional forms. Therefore, the force within the fourth dimension of the unit sphere may be expressed as follows. Given that the Navier-Stokes equations sum the negative forces of both charge and mass, it was first necessary to formally unify the forces of gravity and electromagnetism to facilitate such a summation. Thus, Johnson's entrophitic equation of force unification, or Johnson's law of vorticity, which is given by the following equation. The density times acceleration term proves to be inadequate in expressing both the hydrodynamic and gyrodynamic nature of the physical environment in which the Navier-Stokes equations operate. To this end, a flow rate term is substituted for the quantity density times acceleration, yielding an expanded version of Ashton's law, which is given by the following equation. Therefore, the mass continuity equation, factored by the velocity, which in this case is the speed of light, may be expressed in terms of a flow rate, which is given by the following equation. Therefore, flow rate, as Ashton's law, the mass continuity equation, and Newton's second law, which in this case is expressed in terms of density, may all be combined into one composite equation, which is given by the following equation. This utilization of flow rate allows the Navier-Stokes equations to be expressed in terms of the Quaternion rotator, which is given as follows. Or conversely, but equivalently, we may also state the following. Turbulence is given by the following equation. In this particular expression, Johnson's law of vorticity operates as turbulence. The active and reactive gyroscopic couples are the gyroscopic expressions of the mass continuity equation. Consolidating terms, we may algebraically express the Navier-Stokes equations and several of its various iterations. And there you have it, a complete dimensional explanation of the Navier-Stokes equations.